Okay, so the first talk this session will be given by Pranshu on expectation in stochastic games with prefix-independent objectives.
Okay. Hello. Okay. Thank you for coming for the post-lunch session. So I'm going to talk about my joint work with Laurent and Shibashis. This was accepted in Concur, and it's happening next week. Uh, uh, Yes, yes. Yes. And it was published just today. Okay. So I'm going to talk about expectation in stochastic games with prefix-independent objectives. So first I'll start with some motivation. Okay, so you may come across some systems in your some systems in your life, such as like a Roomba or a spaceship controller. And these are like very critical systems. You don't want your robot cleaner to stop working. Okay. Yes. So our work deals with like given a system and a specification, you want to formally verify that okay, your system works according to specifications. And okay, so I'll be talking about a robot cleaner. So this is our system, and on the right hand side I'll talk about how we model it. So you have a system with various states and transitions. So it can have states like it is sweeping, it comes across an obstacle, it is cleaning, it goes to charging, and so on. So various states, we represent it as vertices in our directed graph. So this is a directed graph. We'll also call it a stochastic game. You can some states are reachable from other states. We represent those as edges in our graph. Okay. And how does the state of the system change? So you have a controller chip inside your system that can take decisions. So it can say now change your mode, things like that. You can have some things in your environment that cause the state of your system to change that are not within your control. And sometimes some things happen randomly, like some bit may flip, or some like you may have some event with some probability of success. So there are three different ways in which your states can change. And diamonds. So and we are now, from now on, we'll view this system as a game between two players, between the controller and the and this is how so you have an execution of the system. So the state of the system keeps changing over time. And we represent that as a path in the graph. So you are moving, as the state of the system changes, you are moving along the graph. And we are interested in systems which never terminate. So like a robot or a spaceship will keep moving forever. So we will get infinite paths. I'll represent them by pi, and they are an element of V omega. So you're given some system, your system is given some specification, all right? Like it should always, your robot should never like run out of battery. You should always go to the charging station like every 10 minutes. So a specification like formally is now an objective of the player. We represent it by phi. So it takes in a path, an infinite path, and returns a rational number. So for each execution of your system, it assigns quantitatively a value to it. Like a higher number is better for the system. And we would like our system to always satisfy the specification. And now what is in your control? So the controller can control the policy. So based on what states have been seen so far, and what the current state of the system is, you may take a decision based on that. So in the game semantics, we call that a strategy of the player. So you see a finite path, and let's say your player is currently in a circle vertex. So your strategy sigma circle will look at this finite path and will return to you another vertex to go into. So this is what we mean by a strategy of the player. Is this clear? Okay. Okay, so I'll talk a bit more about the objectives that we look at. So again, an object, yes, so for it could be randomized, but for this talk it will be deterministic. So an objective is a measure of how good a play is for the circle player. So higher number is better for the circle player. So some objectives that you may be aware of, like we can look. So I have given some examples of Boolean objectives such as reachability and Bushi. So you're given some target set T of your vertices, and your reachability simply says your execution reaches that some vertex in the target set eventually at some point in the future. And this is a slightly more stronger condition which says your execution should keep visiting that target infinitely often. This is Bushi and this is reachability. So like for a robot cleaner, this might be a more relevant objective, such as you should keep cleaning one spot. Like it should not happen that after a point you never clean a spot. So this is intuitively this is what that illustrates. These are some special cases of quantitative objectives. So this is a quantitative objective in general. Boolean objective is a special case of that. So we will look at quantitative objectives today. And in particular, we'll look at a special class of objective called prefix-independent objectives. So you're given an execution. These are a special kind of objective that remain unchanged upon adding or deleting finite prefixes to your execution. So let's say you have an execution v0, v1, v2, and so on. Like if you delete any finite prefix, or if you keep adding some finite prefix, the value of the function does not change. So this is what I mean by a prefix-independent objective. So if you recall on the previous slide, reachability is not prefix-independent, but Bushi is prefix-independent. And I list some more examples of quantitative prefix-independent objectives. For example, this is first we have the lim-inf objective. So let's say we assign a payoff. Yes.
Change the definition and I say that you can add or delete a finite number of symbols somewhere.
Okay, or anywhere.
Yeah, would that change anything?
And your value of the function should remain the same. Is that what you want? I think that may be too strong. Oh, okay, no. Okay, you're deleting finitely many vertices. Okay, then you look at the last vertex that you deleted and you delete the entire prefix before it. You're still deleting a finite prefix. Oh, then I think it may be. Okay. As long as you're adding or deleting finite things, you take the biggest prefix containing all of that, and you delete it, it's giving you the same value. So it should be the same. So these are some objectives that you could look at. We today have a general framework that will work for a wide class of quantitative prefix-independent objectives. What's the time? Okay. So what do we want? Okay, so we looked at objectives, we looked at policies. So what we would like to do is to maximize the output of our system in expectation. So let's say you fix a strategy of both players, circle and square. What do you get? You get a distribution over the runs in your graph. All the decision making is abstracted away in these two strategies. Once you fix two strategies and you let the system run, you get a distribution over the infinite paths in the graph. And under that distribution, if you take the expected value of this quantitative, this rational valued function phi, then you get this quantity. That's the expected value of the objective phi under this distribution of the strategy profile, sigma circle and sigma square. So you fix two strategies of the players, and this is like this quantity is the expected value of the outcome. And what we are interested in, as like looking at it from the perspective of the circle player, we want to maximize the possible expected value of the outcome irrespective of how the square player plays. So this is what it comes down to. So we are now quantifying over all strategies of circle and square. So this is the same quantity as before, the expected value of the outcome of circle and square. But this is the infimum over all strategies of square, and this is the supremum over all strategies of circle. So this is intuitively, it is the best value that circle can ensure irrespective of how square plays. And our decision problem that we look at today is this. So you're given a game, a vertex, some prefix-independent quantitative objective, and some rational lambda. We ask, is the expected value of V at least lambda? So this is the decision problem that we look at. And here I write another decision problem, which is a bit different. So you're given a game, a vertex V and a threshold lambda. You're asking, can circle ensure with probability 1 that the value of your outcome is at least lambda? So here you are saying with probability 1, is it at least lambda? And here you are saying, is the expected value at least lambda? So if you satisfy right, you also satisfy left. Okay. And in both cases, if the answer is yes, then we would like to synthesize a strategies for the circle player that achieves this. Okay, so I'll say that the right side problem, we showed it in a previous paper that was accepted last year in FOSAX. So we'll use the right side problem as a subroutine for our left side problem. All right. Okay, so yes. Could you repeat it? Yes. Yes, so conceptually, the almost sure problem feels like an easier problem. We'll have many instances of the almost sure problem to solve our expectation problem. Yes. Okay, so this is the overview. So you're given an expectation problem and we want to characterize it in terms of the almost sure problem. And so this problem for the expectation problem has been shown for Boolean prefix independent objectives such as street and parity in this paper. So if and now what we did was we extended this technique to quantitative objectives. And the overall idea of our algorithm is the following. You simply guess the value of every vertex, and then our contribution is to give an efficient verification of the guess. So let's just guess. So let SV denote this expected value of vertex V in game G of function phi for V, and we write this as a vector, SV1, SV2, and let's say n vertices, so SVN. So this is the correct value vector, and now we guess some RV for every V. We guess some value for every vertex, and now all we need to do is we need to verify if these vectors are equal. We don't know this S, like a priori. Okay. So now we give a, okay, first we look at how to visualize this vector. So you are given this vector R, which is basically just listing down the guessed value for every vertex. Now what you do is you may have several vertices where you guess the same value. You collect all of them into the same value class. So I'll write them with capital R. So capital R1 is like one class where all vertices have the same guessed value. This is another class group of vertices where all vertices have the same guessed value and so on. And let's say we write it in increasing ascending order. Okay. I can look at an example now. So this is an example of a stochastic game. And let's say we guessed this. So for convenience, I already drew it so that the vertices that we are going to guess with the same value are drawn close together. So this, let's say we guessed this vertex as value -10. We guess all these vertices are value -5 and so on. I've written the guessed value of every vertex and there are 5 value classes. We do some we'll do some modifications to this. First, I'll show that these are some special vertices. So these are diamond, the probabilistic vertices. So if you have a probabilistic vertex with some out neighbors in a different value class, we'll call them the boundary vertices, because once you reach there, you may be thrown out to a different value class. All right. So I have highlighted the boundary vertices. And then what we do is now we'll restrict each value class. We'll restrict the game to instances for each value class. So now we get one instance of a game for every value class. And what we'll do now is intuitively, we'll solve the almost sure problem inside each of these restrictions. Okay. And here is our main result. So if you have a value vector R, you guess this vector R, it is equal to the correct vector S if and only if R satisfies the following 3 conditions. There are 3 conditions. That's called Bellman lower bound and upper bound. I'll write this in a future slide. But let's look at this condition first. So for every vertex V, if this holds, then we'll say that R satisfies the Bellman condition. And what is this? This is simply saying you look at a vertex V. If it is a circle vertex, its guessed value must be equal to the maximum over all guessed values of its out neighbors. Otherwise, if you have a square vertex, the guessed value of V should be the minimum over the guessed values of all out neighbors of V. And if V is a diamond vertex, a probabilistic vertex, it should be a weighted sum of all the guessed values of the out neighbor of V, where the weights are according to the probability distribution in your stochastic game. And this is one of the conditions. So so intuitively it makes sense, because if you have a vertex V that belongs to circle and you look at all of its out neighbors, circle would like to go to the vertex whose value is the highest. What happens in one step doesn't matter because it's a prefix-independent objective. So you can just go to the vertex which has the highest value and start playing from there. So this is where prefix-independent comes into play. And this is one of the conditions needed to show that R is equal to S. And there are some interesting consequences of this, of R satisfying this condition. So if you look at any boundary vertex, and suppose R satisfies this Bellman condition, then it will have an out neighbor in a class that is smaller, and it will have an out neighbor in a class that's higher, because it's the average of its out neighbors. And there's also a corollary here that there will exist some classes without boundary vertices. Now, why is that? You look at the class with the least value. It cannot, if it had a boundary vertex, then it would have had an out neighbor in a value class with an even smaller vertex, which cannot happen. So in particular, the minimum and the maximum value classes won't have boundary vertices. There may also exist other value classes without boundary vertices. So this is one consequence. Another more interesting consequence is the following. Suppose the players play in the following way. Whenever the token is in a value class, let's look at circle player. Let's say he always moves the token to another vertex in the same value class. Then this can in fact ensure that the play eventually reaches some value class from which it never exits. So what I've written be the case that the play keeps jumping between value classes forever. With probability 1, it will eventually reach somewhere and stay there forever. It's not necessary that it be a class without boundary vertices. Yes. So no matter how square plays, circle can ensure that it will be stuck in some value class eventually. And Why is that? So you see, because of the Bellman condition, all the circle vertices can only have out neighbors in the same class or on the class to the left, because the value of a circle vertex is equal to the max of the value of its out neighbors. So there is no transition from a circle vertex to the right, and there is no transition from any square vertex to the left. So what will happen is, let's say the circle player always keeps moving in the same class. Like you may reach the boundary vertices some finite number of times, and you may keep moving, but eventually what will happen is either you reach a class without boundary vertices, or you will end up in a class where square can ensure that you never reach the boundary vertex, and square also never leaves the value class. So in that case, neither the square nor the circle is leaving, and hence the play remains in that value class forever. Okay, so these were two consequences of the Bellman condition. And finally, now we'll come to the other two conditions that I had skipped. So again, a guessed value vector R is equal to the correct value vector S if and only if it satisfies the Bellman condition and these two conditions. So these are like duals of each other. So it's okay to just focus on one. So what have I written here? So for every value class, so there are KR value classes. For each value class, you look at each of those games. The circle player can almost surely satisfy this objective. Like now it's just you want to satisfy phi is greater than some threshold. That's the value of guessed value of that value class from all vertices in that restricted game. So this was the right hand problem that I was talking about. So circle, we need to verify circle can almost surely win this almost sure problem in each of those value classes. The dual is we need to check if square can almost satisfy phi less than some threshold in the trap subgames from every vertex. So if we can verify these three conditions, then we have verified that R was the correct guess, and it's an efficient translation. So Bellman, you can simply just look at, you just construct this, you just look at whether circle has all of its neighbors in the same and left. So these are easy to verify. Bellman can be verified in polynomial time. And okay, so what is the idea behind this lower bound condition? So this is the key idea, key takeaway, that the token eventually reaches some class from which. Okay, the key idea. 1 minute. So the key idea is token eventually reaches a class from which it never exits. That was a consequence of Bellman condition. And once you reach a class from which you're not exiting, so in that class, circle can ensure that the phi value of the outcome is at least some Ri minus some small number with probability 1. So if you take the weighted sum over all the value classes you eventually end up in, you get the correct expected value of your original class. And finally, we have the complexity that this problem is in NP to the A intersection co-NP to the A, where A is you have an oracle access for the almost sure satisfaction problem. And moreover, in our paper, we also show that the memory size to play optimally for the expectation problem is no greater than the memory size required to play optimally for the almost sure satisfaction problem. So in summary, we gave this characterization for quantitative objectives, prefix-independent objectives in terms of the almost sure satisfaction. And that epsilon, we showed in the paper how to derive that for some common objectives. Can discuss offline, or you can have a look at the paper. And in the future, we would like to see if we can implement some of this efficiently practically. Okay, thank you.
Does anyone have any questions?